Hi, I'm back with another in the series where I build experiments from Charles Platt's excellent Introduction to Electronics, Make Electronics, the third edition. And today the book has me building a reaction tester. But before we get on to that, here's a quick introduction to two new components that will be introduced in this experiment. Now, in electronics, as in nature, occasionally two species form a symbiotic relationship, and that is certainly the case with the species Lux segmentum, commonly known as the segmented LED display, and Decennium numerare, commonly known as the decade counter. And as you shall see, joking aside, these two used in combination allow us to very easily build numeric counters from 1 to multiple digits. So let's have a look at that. So this is not the full reaction tester circuit yet, although we have already added to the board the 3 multi-segment LED displays, and each one of those is paired with a 4026B decade counter. You'll also notice there are 3 555 chips on there. At the moment though, just for a test, we've only wired up one 555 with the first decade counter and the first multi-segment display, just to check that everything is working. Now, I have deviated from the circuit in the book a little bit with this. One thing I've done is just up the value of one of the resistors in the RC network, just because I found the count was a bit too brisk for my liking. The other thing I've done, as you'll see, is put the button onto a little breakout board here. The reason for that is because my buttons are bigger than the ones that the author seems to have access to, and this is going to end up being a very full breadboard, and I will run out of room if I try and squeeze the buttons on there as well. So I've put the button, and there'll be more added to it on this breakout board. And the other thing is, quite frankly, it's much easier to push a button on a breakout board like this than try and poke your finger in amongst a forest of other components and potentially short something out. Okay then, let me start this up and show you what this test circuit does. So what you can see there is that the multi-segment LED display counts up the numbers from 0 through to 9 and then just repeats, and it will go on ad infinitum. And what's causing it to transition from one number to the next is basically the output from this 555 here. And hopefully, if you've watched the earlier episodes in the series, you will now recognize that this is wired in astable mode. The giveaway for that, of course, being this little green wire that's connecting the threshold pin to the trigger pin. So if I press this button, this will reset the count. So you can see it's gone back to 0 there. As long as I hold it down, it will hold on 0. As soon as I release it again, it will start the count. Okay, that's enough for this demonstration. Let me explain how this is working. So this is a simplified version of the circuit. I've ignored all the connections on the 555 except for the output pin, pin 3. If you're not sure how a 555 works, please watch the video for experiment 15, which explains it in detail, and I'll add a link to that in the description. So let's move on to the 4026B. As with all chips, it needs power, of course, and in this case, pin 16 is connected to the positive supply and pin 8 is connected to ground. The decade counter maintains an internal count, which is set to 0 on startup. Internally, it's not actually represented as a number as such. Instead, it uses an optimized type of counter called a Johnson counter. But for now, it's easier to think of the counter holding a number from 0 to 9. You can Google Johnson counter if you're really interested in how it works. So that count will be incremented, or more correctly, will transition to the next state whenever the clock pin, pin 1, detects a rising edge. and that's a transition from a low state to a high state. Note that the output pin, pin 3 of the 555, is connected to the clock pin on the 4026. And because the 555 is wired in astable mode, it will generate a regular pulse wave. And because the start of each pulse is a rising edge, that will trigger the 4026 and cause it to increment the count at the start of each pulse. And after 9 pulses, as you've already seen, the 4026 will of course wrap around to 0. So how does this internal count show up as a digit on the LED display? Well, note that the segments of the display are labelled A to G. The LED display has a pin for each of those segments, and setting the pin high will light the corresponding segment. So, for example, if we set pin A to high, then the horizontal segment at the top of the display will light up. So for each digit, the 4026 has to work out which segments should be set to high to show the correct number on the display. If the internal count was 1, for example, then segments B and C would be set to high to form the shape of a numeral 1. Now in this video, I'm not going to go into detail about how a Johnson state, and remember that's the internal representation of the current digit, is translated into the correct state for each segment pin. But suffice it to say, it involves something called Boolean logic, and that's a topic that we'll be exploring further in the next video. Note that if pin 3 display enable is low, the 4026 will not send a signal to any of the segments until it's high again, even though the internal count will be maintained. And one reason you might want to do that is to save power. Imagine if this was a display on an equipment panel in a factory, for example. Maybe the engineer responsible for that equipment only needs to see it periodically when she's running diagnostic checks, let's say. So rather than run the display continually, which would just be a colossal waste of power, you'd simply provide a button or a switch for the engineer to activate the display only when she needs it. For this circuit, we do want to see the display at all time, so this pin is simply connected to the positive supply rail to keep it high. The pin next to it, pin 2, the clock inhibit, is normally expected to be low, but if high, it will cause the 4026 to ignore any triggering at pin 1 and simply hold the current state. Now in this test circuit, we keep it low by connecting it to the ground rail, because we do want the digits to advance at the start of each cycle from the 555, but we will see a use for the clock inhibit pin a little later in this experiment. Finally, we have the reset pin. This is normally expected to be low, but if it goes high, it will reset the count to 0 and will hold at 0 until the reset pin is low again, at which point it will continue counting. Now we use a pull down resistor to hold this pin low, but as you saw in the circuit demonstration, we also have a button that when pressed connects this pin to the positive supply rail, thus driving it high and causing a reset. Now note that the LED display has 2 ground pins, and this is simply for convenience. They're both identical and it's just so that you can connect to ground on either side of the display. We're using the one at the bottom, and you can see that we're connecting it through a resistor, and that's acting as a current limiting resistor, because remember, even though this type of LED looks different from the LEDs that we've used before, it still has similar characteristics and it's still subject to being damaged by too much current unless we protect it with a current limiting resistor. Now, because there's a common ground pin, we can just use a single resistor to protect each segment. Now, you might be wondering, okay, counting from 0 to 9 is great, but what if we want to count to 99 or 999? How do we do that? Well, it has something to do with one of the pins that we haven't looked at yet, and it's a problem that will be solved in our complete circuit. So let's look at that next. So here's the finished reaction test circuit, and you can see, as before, I've put all of the buttons onto a little breakout board. And to be honest, even if you've got the tiny little buttons that the author seems to use, I would still suggest doing things this way. You can see from where these leads end up where the original placement of the buttons was on the circuit board. And I'm sorry, but there's just no way, even if you've got the slenderest fingers and the greatest dexterity in the world, that you're pushing a tiny little button placed there without either shorting something out or pulling something out of the breadboard. It's just not happening, especially when you're trying to activate it quickly, given that this is a reaction test circuit. So I would suggest, even if you've got those small buttons, do what I've done here. Use a little breakout board. It would be much easier to play the game that way. So one thing you'll notice when I apply power is that the counter starts running straight away. And that's an unfortunate side effect of the simplicity of the circuit. So what we need to do to prepare to play the game is firstly stop the counter and then press the reset button to zero it. Now we're ready to start playing the game. So the way it works is we press the start button. You notice the yellow light has come on. I'm waiting for that to go off and the red light to come back on. That is my cue to press the stop button as quickly as I can to check my reaction time. But what I just want to show you is that these digits are working. So as this one reaches 9, that one flips over, and hopefully you just saw that the same thing happens with the third one. And these are supposed to be counting milliseconds, but obviously at the moment we've got higher values in the RC circuit, so that we're not getting anything like milliseconds, and we'll fix that in a short while. What would actually happen is, as soon as I saw that light change back, I'd hit the stop button and then I'll be able to read my reaction time in milliseconds on the display. So here 282 milliseconds that would be. And then if I want to play again, I can simply press the reset button, set everything back to 0, and then we can start again. So before we go on to fix the timing issue, let me just explain exactly how the decade counters and the displays are wired together to get that count working properly. So again, this is just a very simplified diagram just showing the important wiring between two of the 555s and the three 4026B decade counters. So as you've already seen, the timer 555, the one that's wired in a stable mode, is what's responsible for sending those clock pulses to increment the count. And that's just sent through to the first 4026. So how does that count then propagate to the other two 4026Bs and the displays that they're connected to? Well, that's where this pin that we haven't yet looked at comes into play. This is the carry pin. And basically, this pin is set to high whenever the 4026B clocks over from 9 back to 0. So each time that happens, we get a positive pulse from this carry pin. So by connecting that carry pin to the clock input of the next 4026B, each time this one clocks over from 9 to 0, this one will get a pulse to increment it. So if this is at 1, when this clocks over from 9 to 0, this will then move up to 2. And again, we can chain additional 4026Bs in the same manner to give us as many digits as we need. So exactly the same thing happens here, so that we've got our units, our tens and our hundreds. What happens when we want to stop the count? Well, you remember we talked about this clock inhibit pin, and normally this is held low, but if it's held high, then it will stop the 4026B from responding to any pulses it receives at the clock input. They may still be happening, but it will just ignore them. So what happens with our stop 555 is in a stop state, that output pin there will be high, which will hold the clock inhibit high of this first 4026B, and that will prevent it from recognizing any input from the timer 555, and it would just hold the count steady. Now, of course, we don't need to connect to the clock inhibit of either of the other two 4026Bs because they are both dependent on the count of the first one incrementing for them to increment. So as long as the count is stopped in this first one, we know that it can't ever increase in these two. And therefore, we can just hold the clock inhibit low for both of those chips because we always want their clocks to be active. That just leaves us then with the wiring for the reset. And here you notice that this is different from the clock inhibit because here we do need to connect to each of the chips. So basically we connect the reset pin normally to ground to hold it low, but we have a button, our reset button, which can momentarily connect it to the positive supply rail to drive it high, which will cause all three chips to reset at the same time. So there you go. That's how our 4026Bs are working together to give us that 3-digit count. So how do we solve the issue with the timing? Well, the first thing we can do is to get the values of the components in the RC circuit somewhere in the right ballpark. And remember, we need these to give us a pulse of exactly 1 microsecond or as close to that as we can get. So if I connect the power, you will see that the delay is indeed a lot shorter than it was. In fact, it's so short now, the figures are changing so rapidly that our eye can't register the changes for the first two displays. But they are in fact changing, and I can prove that simply by stopping the count. There we go, we've got 138 there currently. So let me start things up again. You can see that the delay is somewhere in the right ballpark. But of course, because component values are not exact, it's going to be difficult to hit that exactly. So we need a way of fine-tuning it. And to do that, the author has added a trim pot into the circuit to act as a variable resistor, and that forms part of the RC network. But we also need a way to help us calibrate that timing and ensure that we're hitting the right mark. So to do that, we have this temporary LED here, and that's connected to the carry out pin of the 3rd decade counter. And you'll recall from the previous explanation that that will go high every time this counter wraps around from 9 to 0. And of course that should happen once every second. Each time the full 3-digit count wraps around from 999 to 000, that LED will flash. So if we can adjust things so that that LED is flashing exactly once per second, which we can do with the aid of an external timer, then we know that we've calibrated the circuit successfully. Okay, so I've calibrated everything now. I've removed that extra LED now that we no longer need it for calibration. So let's give this a go for real and see how awful my reaction times are. Oh, 198 milliseconds. Yeah, I'm happy with that. Could be worse. Okay, so there you go. That's the reaction test circuit. And in the next experiment, the book introduces us to the really important concept of Boolean logic and expands our palette of integrated circuits by also introducing the logic chips that we can use to implement it. And implement it we shall by using those chips to build an electronic lock. Sounds good? Then please join me for the next episode. See you then.